Hello everyone, welcome to this presentation. This time I'm going to talk about wireless power transfer using inductive power transfer and based on non-resonant converters. Most of the material that I'm going to present today has been published in this paper entitled Analysis, Design and Evaluation of a Zero Voltage Switching Non-Resonant Converter for IPT Applications that we have published in IET Power Electronics. Okay, and here is the information for this paper. The outline of this presentation is this one. We are going to see an introduction, then the analysis of non-resonant inductive power transfer systems, an example, some simulation and experimental results, a comparison with a resonant IPT system, and finally some conclusions. Okay, just a quick review of an IPT systems. As you know, we have two coils. We are injecting energy into one coil and generating an electromagnetic field, and this magnetic field is going to transfer energy to a secondary coil, and this secondary coil can transfer energy finally to the load. We know that these type of systems can be modeled using this equivalent electrical circuit here with these series inductances and these voltage sources depending on the derivative of the currents. Okay, these here are the differential equations that gives the behavior of this type of systems. Okay, we know that here L11 is the self-inductance of coil 1, L22 is the self-inductance of the second coil, and M is the mutual inductance between both coils. Okay, so this is the equivalent circuit. We have other possibilities for modeling this type of circuits. For example, the T-type model is also very used, and then we model the circuit with these three inductances, L11 minus M, L22 minus M, and then the parallel inductance with the mutual inductance. Okay, typically when we are supplying this type of systems, in order to adapt the input voltage and the load with in the middle with these IPT systems, we need some kind of compensation. Here in this slide, we show the four most common types of compensation that we can find in the literature. We have the series circuit with two series capacitors that are going to operate at the resonant frequency. Okay, the circuit is going to operate at the resonance frequency in these circuits. Or we can have the series at the input and parallel at the output, parallel at the input and series at the output, and parallel at the input and at the output. At the end, this depends on the behavior that we have, that we wish to have at the input and at the output. If we want a voltage behavior, then we use the series compensation, and if we want something like current source at the input, voltage source at the output, then we use a parallel at the input and series at the output, and so on. Okay, so this is the common circuit that we can find in the literature. Okay, but what we cannot find so commonly is the question, the following question when we are working with these systems. And the question is, why do we need to use these resonant compensating circuits? Can we do the same thing using non-resonant operation? Okay, so this is the question that we are trying to answer in this presentation. So we can think of a non-resonant inductive power transfer systems that will be like this one. In this case, we are not going to use a resonant compensation. We use the half bridge circuit here. in order to generate a square voltage that we are going to apply to our IPT system. Okay. In this case, capacitor C1 is not a resonant capacitor; it's just a DC blocking capacitor. So here B1 is going to be a square waveform, okay, with maximum value of plus DC divided by 2 and a minimum value of minus BDC divided by 2. Okay. So here we are applying directly the square waveform to the IPT system. And then same thing at the output. We don't use a resonance at the output. We use a secondary stage in order to generate the DC voltage at the output. And this can be done with several possibilities. One of them is using a simple rectifier with 4 diodes and then a filter capacitor and the load. We can use a doubler in order to increase the voltage at the output, or even we can use a quadrupler so we can generate more voltage even at the output, 4 times, theoretically 4 times the voltage that we have at the input. Okay, so this is the idea. If we can use this type of non-resonant circuits in IPT systems. So in order to study this, what we are going to do to facilitate the analysis is, instead of using the T-type equivalent circuit that we have seen at the beginning of this presentation, we are going to do a transformation and obtain the equivalent P-type circuit with these 3 inductances, LA, LC, and LB. We can do this using these equations here, in which we can obtain these 3 inductances as a function of the T-type parameters, L11, L22, and Lm, which is the mutual inductance that we have seen before. It's also called Lm or M. Okay, so in this circuit we are applying an input voltage which is a square waveform at the input, okay, that we are going to designate as V1, and then we are going to have also here at the output another square waveform, okay, because it's the input waveform to the rectifier or to the multiplier that we are going to use, okay. So here the voltage is going to be a square waveform, but the phase is going to be given value in comparison with the phase of V1. So we are taking the phase of V1 as the reference phase, and then at the output we are going to have this square waveform with a given phase phi. Okay, and the same thing in this equivalent circuit, which is easier to study because here we have the inductances directly in parallel with the voltage sources. So these 2 currents, ILA and LAB, are easier to calculate. So by analyzing this circuit, we can obtain everything. Okay, for example, we are going to have the input voltage V1 here, which is going to be this square waveform at the input. We are going to have the voltage V2, which is another square waveform with a given phase between them. Okay. Usually V2 is going to lag V1 because it is an inductive circuit. And then, as we have said before, ILA and ILB can be immediately calculated from the voltage sources. Okay, so we just have to calculate ILC, which can be calculated obtaining the voltage here. Okay, VLC, which is the difference between the input voltage and the output voltage, and is going to be a square waveform with something like a square waveform like this one, okay, because it's the difference between these 2 voltages here. Again, if we do all the calculations, we can see that ILA is going to be this triangular waveform, because at the end is the current through this inductance here, which has a square voltage source applied to it. Okay, same thing with ILB is going to be something like this. Okay, and then if we calculate I2, then which is the output current, is going to be something like another triangular waveform, and same thing with ILC. Okay, everything is done in this paper that I have shown at the beginning of the presentation, and all this is calculated there. Okay, so then we have here the output state, the output stage, the rectifier and the multiplier. So what we are going to have at the output here, I2 is going to be and the rectifier, the rectified current, okay, of I2, and the average value of this current at the end is the current circulating through the load resistance, okay, because the harmonics are going to be filtered by the output capacitor. So by analyzing this circuit, we can obtain then the voltage gain and also the phase of the output voltage, which is another important parameter. Okay, so the voltage gain that we are going to have is the DC output voltage divided by the voltage V1 that we are applying here, the peak voltage of the square waveform. Okay, and it is this expression what we are going to obtain. And the voltage phase, which is this angle phi, but here expressed in time, not in degrees, which is at the end is the same, then follows this expression here. Okay, and as we have seen, these two expressions depends on the parameters alpha and beta, and these two parameters are expressed like this. Okay, as a function of the inductance LC, the switching frequency, the load resistance, and also the inductance LV for the parameter beta. Okay, depends on LV and LC. So this is quite straightforward. So with this we can even design our circuit. If we do a representation of the voltage gain as a function of these two parameters, alpha and beta, we have these curves, okay, that provide us with this value of the voltage gain, so we can do our design based on these equations. Okay, same thing with the voltage phase, okay, the output voltage phase. So we can obtain these characteristics and obtain the phase angle that we are going to have. Also, in this kind of systems, it is very important to obtain the value and the phase of the current I1, because this current at the end is the current that is going to be circulating through the switches of the half bridge. Okay, so here we have the two equations corresponding to I1. Okay, we can calculate I1 as the addition of ILC plus ILA. Okay, so we can calculate I1, and these are the expressions in time, and from this we can obtain the phase of I1, okay, in time, which is the time to T1, and also the peak value of I1, okay, I1M, which is the peak value of this. Okay, at the end, I1, as I have said, is the addition of ILC, this triangular waveform, plus ILA, which is this other triangular waveform. Okay, now some an example of this circuit type of non-resonant circuit. We have used these inductors for the implementation of the IPT systems, okay, from Würth. And then we have, and this is one of the inductors, we have used two of them, and this is in this photograph, we can see the implementation of with one of the inductors on top of the second one, and then we have our IPT system. Okay, we have characterized this IPT system as a function of the gap between the two elements. Okay, and then we obtain the values of the three inductances corresponding to the pi circuit. Okay, so we have here LA and LB and LC obtained as a function of the gap in the circuit. Okay, so we can see the evolutions when we are increasing the value of the gap in millimeters. And this allows us to perform different analyses and simulations with different values of the gap. So with this IPT system, and also with the characteristics that we have obtained before, we can calculate the output voltage versus the switching frequency for two values of the gaps. Okay, so we can see the output voltage here as a function of the switching frequency from 360 kilohertz to 440 kilohertz. With a gap of 0 millimeters, so we have a voltage like this one when we use a rectifier. Our target output voltage was 5 volts. Okay, so we have looked for a switching frequency that allows us to get this value. Okay. If we use a doubler circuit, then we need to decrease the switching frequency in order to have output voltage around 5 volts. Okay, and same thing with if we use a quadrupler, then the switching frequency must be lower, even lower, in order to obtain these values around this required point of 5 volts. Okay. For a gap of 5 millimeters, then we have these other characteristics which are also very similar, and this has been obtained for a load resistance of 5 ohm. Okay, so we are going to have around 5 watts at the output. So now, in order to check our design, we have performed this simulation in LT-SPICE. As you can see, we are implementing here our IPT system using the pi-type equivalent circuit. Note that this capacitor here is a DC blocking capacitor, is not a resonant capacitor, it's 33 microfarads. So what we are going to have here is a square waveform voltage with a peak value of 12 volts, okay, because we are supplying our circuit with 24 volts. Okay, and we are operating at 370 kilohertz. Okay, so if we look here, is something like this point. So we are going to have something like this value, around 5 volts. Okay, and the time that we have used in the gate signal, between the gate signals of our half bridge, is 250 nanoseconds, and we can see here, and these are the definitions for our pulses that we are injecting into the gates of our transistor. Okay, so we are including here the delay time, the dead time between the both pulses. Okay, so we have also the series resistance of the inductors, and we have the full bridge rectifier here at the output using Schottky diodes, and then the capacitor, the filter capacitor, and the load resistance. In our case, the load resistance is 5 ohms. And then we are performing a transient simulation for 200 periods, switching periods, and saving information, saving waveforms of the last 5 periods. And the step of our simulation is 50 nanoseconds. Okay, we will talk later about these calculations. So we can see here the waveforms of the gates, okay, the gate in the one of the transistors and in the other transistor at the top and at the bottom. So we can see that we have some dead times and the waveforms are quite good. We have also here the square waveforms, the voltage that we are applying at the input of our IPT systems. Okay, so this is this square waveform after capacitor C2. Okay, so it's a maximum of 12 volts, a minimum of minus 12 volts. And in green, we can see the current at the input, IR1, okay, the current that is circulating here at the input. So we can see that it is the triangular waveform with two different slopes as we have seen in the analysis. So we can see also that we are providing zero voltage switching, okay, because we have here a negative current, enough negative current before the applying a positive current here, and this is going to provide zero voltage switching, okay. In this interval here, in this first interval, when we are applying this voltage at the gate of the top transistor, it is conducting the antiparallel diode of the transistor, okay. So then the current naturally goes to positive and goes through the channel of the transistor. So we are having here zero voltage switching, okay. And also with the dead time that we are providing between these two gate signals, we can decrease almost to zero the losses during the turn off of the transistor, both transistors, because we are sending the energy into the parasitic capacitances, the output capacitances of the transistor, okay. So the current at the end is used to charge and discharge these capacitances and provide also operation of these capacitances as loss-free snappers, okay. We have calculated here the RMS value of the current, and we have obtained this value 1.47 amperes, okay. And the output voltage is 5 volts, as we can see in this waveform at the bottom. So even with these calculations here, what we have done is an estimation of the efficiency of our system in simulation, okay. So here we are calculating the output voltage as the average voltage between these 2 points, okay. Then the input power, which is the product between VCC is the input voltage, times the current circulating through the voltage source. Also the output power, which is the output voltage to the squared output voltage divided by the resistance, and the efficiency is the ratio between the output power and the input power, and then also the losses is the difference between input power and output power. Okay, so we can see here that we have obtained an efficiency of 77%, okay, which is not very good. But we have to take into account that this is a very low power system, it's only 5 watts. The current that is circulating here is about 1 ampere. So we have a lot of losses here. Most of the losses are in the output rectifier, okay, because we have here the current of 1 ampere within half semi-period, and usually the voltage here, in the diodes, Schottky diode, is around 0.4, 0.5 volts. So we are going to have something like 250 milliwatts in each diode, okay. So it's around 1 watt in the rectifier, okay. So the total power loss is 1.5, around 1.5 watts, okay. So this is the efficiency that we are getting in this case. These are some experimental waveforms of using the rectifier with no gap, with a gap of 0 millimeters. Okay, so we can see the gate voltage. Okay, again in the gate voltage waveform, we can see that we have no Miller plateaus. Okay, so this is an indication of that we are obtaining zero voltage switching and good switching with very low switching losses. Okay, and then we can see here the waveform I1, which is the triangular waveform, very similar to the waveform that we obtain here with a peak value of 2.5 amperes. Okay, so it's the same value that we are obtaining here. And this again, this is the square waveform that we are applying to our IPT system, and this is again the same current I1. Okay. And this is the efficiency versus the output power in different situations for two gaps of 0 millimeters and 5 millimeters when we are using a rectifier, a doubler, and a quadrupler. Okay, all of them for a load resistance of 5 ohms. So we can see here that the efficiency is something like 80%. Okay, very similar to the values that we obtained in the simulation. If we use a doubler or a quadrupler, then the efficiency is going to decrease, okay, because we are going to have more current circulating in our circuit. The triangular waveform, the amplitude of the triangular waveform is going to be higher, and then the losses are higher. Okay, and this is the situation for a gap with 5 millimeters. The situation is very similar, only that we are going to have even lower values of the efficiency. So this is a comparison with a resonant IPT system. What happens if we use, instead of non-resonant circuit, a resonant system? Okay, in this case we're including these two capacitances here, and these two capacitance are calculated in order to resonate with the series inductances. Okay, you have to note that we have used now here again, because we are working with the resonant circuit, we are using the T-type equivalent circuit, which is more interesting for calculating the resonances. Okay, so L1 is going to resonate with C2 and L2 with C3 at this switching frequency, which is 370 kilohertz. Okay. So note that in this case, in order to obtain here at the output the same 5 volts, we have to reduce the input voltage to 12 volts here at the input. Okay, because at the end what we are going to have here is that this series circuit is going to behave as a very low impedance, because this is going to operate as resonance. Same thing with the output one. So at the end, the square waveform that we are generating here, which is going to be between 0 and 12 volts, we are going to have here after the capacitor a square waveform, or we should have a square waveform in between -6 and +6. Okay. And I say we will have, because here C2 is playing two functions, is playing the DC blocking function and also is resonating with the inductance. Okay, so at this point we are not going to see the square waveform, we are going to be a combination of the square waveform and the resonant voltage. Okay, so at the end, in this waveform, what we are going to inject into our system is we have to consider is the first harmonic of this waveform, because the other harmonics are going to be filtered. Okay, so if we calculate the amplitude of this waveform, is going to be something like 4 times 6 divided by P. Okay, and this waveform, because it is operating in series resonance, we are going to have more or less the same voltage here, okay? And the rectifier is going to rectify this waveform and apply a rectified waveform at the output. So at the end, the average voltage that we are going to have here at the output is the average voltage of this waveform, okay? And the peak value of this waveform is this one, 4 times 6 divided by P. This times 2 divided again by P equals the output voltage that we are going to have, okay? And this is something, if we calculate this, is something around 5 volts, okay? So at the end, this could be a disadvantage of the resonant IPT, because once we have fixed our input voltage, there is nothing that we can do to change the output voltage if we operate at resonance. Okay, because when we operate at resonance, we are fixing the output, the voltage here and also the voltage here. So the output voltage is fixed by the input voltage. Okay. While when we use the non-resonant circuit, we have more possibilities, okay, because the output voltage is depending on the different components in our circuit, and then we can design our circuit in different ways to obtain different output voltages, okay. Here, independently of what we do with our circuit, if we operate always at resonance or close to the resonant operation, then we are going to have the same value at the output voltage, okay, and depends only on the level of the input voltage. Let's take a look of the at the waveform. Sorry, we can see here the gate signals again, and the square output voltage, also the resonant current, okay, and the output voltage, okay. So we can see that we are going to have also zero voltage current. In this case, this value of the current is a little bit lower, but we can obtain even zero voltage switching with no problem, okay. One advantage here is that the RMS value of the current is much lower. Okay, it's only 1.15 compared with the non-resonant circuit. In the simulation, we had 1.47 amperes, okay, which is higher. So we are going to have better efficiency with the resonant operation, okay. So we have calculated here the values, and with the same calculations as before, and we obtain here a value of the efficiency of 84.4, okay, which is much better than the 77% that we have obtained for the non-resonant circuit, okay. So this is an advantage for the resonant operation. But another advantage that we can have with the non-resonant operation compared with the resonant operation is that in our resonant circuit, in our non-resonant circuit, we have, better look at this first circuit. In our non-resonant circuit, using this equivalent circuit, as we can see, we have also this inductor here in parallel with a voltage source. So this current I1, at least it is going to be always to ILA, okay? So this means that we have at least this current always triangular waveform circulating through the half bridge. And this could be an advantage when operating at low loads, okay? This is similar situation as in the LLC resonant converter, okay, which is very popular because this characteristic that we can obtain low switching losses when operating at low loads, okay, because we have always some current circulating through the inverters, through the half bridge inverter, okay. So this could be an advantage of the non-resonant circuit. Okay, and then just for the conclusions, we can summarize that it is feasible to use non-resonant converters for inductive power transfer. The output voltage depends on the equivalent circuit inductances and also on the switching frequency. So this can provide more flexibility for the output voltage design compared with the resonant circuit. If we operate always at resonance, then we are going to have always the same value of the output voltage and depends only on the input voltage. Okay, it's going to behave like exactly a voltage source. Also, zero voltage switching can be obtained in non-resonant operation, even at low load, which could be an important advantage. Also, we have a lower component count. We can use one less series capacitor at the output. We don't need this series capacitor at the output. And the main disadvantage of this converter could be the lower efficiency that we are going to have in comparison with the resonant converter. Okay, we can also say that maybe we can have higher EMI because we are using triangular waveforms instead of sinusoidal waveforms. So if we compare the non-resonant circuit with the resonant circuit operating exactly at resonance, then the EMI could be some higher, especially in the surrounding part of the coils, okay, of the IPT systems. Okay, at the input, it could be not so high the difference because at the end, at the input, we have part of this triangular waveform and part of this sinusoidal waveform, so the difference of EMI could not be so high. Okay, this is all now. Please, if you have any question or comment, leave me a comment below and I will be happy to answer any comment from you. This is all for now. Thank you very much for watching this video and see you in another one. Goodbye now.